Alrighty, so for our review, we'll talk about that, and then I wanted to talk a little bit about comparison, the comparison test we didn't get to on Monday, and then we'll work our way back towards arc length and surface area. So in the first one, I'm gonna have to copy this because we're gonna lose it in a second. Okay, where did all of those go then? Here we go. I have to jump around a little bit. Okay, so in the first one, you're asked to, or I asked you to factor this binomial. And you have two options. Well, here I did factor it for you already. One way is that you could just recognize this as a perfect square. This is to the x to the sixth in the first term, 1 over 4x to the sixth. You could think of that as, say 1/4 x to the negative sixth. And the x to the sixth over 4 in the first term, that could be 1/4 x to the sixth. And so recognizing that as a perfect square, the square root of the first term would be x cubed over 2. The square root of the last term would be 1/2 x to the negative 3, or 1 over 2x cubed. And if you FOILed that, you multiply these middle terms together and double it, then the x cubed cancels out with the 1 over x cubed, and 1/2 times 1/2 is 1/4, and you double it, and that is where you get the middle term of 1/2. So that's one way that you could do it. I would recommend that you sort of, as we get into the arc length problems, you'll see this kind of simplification, and this is a good approach to go with. The other way that you could do this is by getting a common denominator. So you could get a common denominator. In this case, you would get a common denominator of x to the sixth. If I did. And keep the 4 down there too. So you could get a common denominator of 4x to the sixth. And then simplifying, combining like terms in the top up here, then you'd be able to see very clearly in the top how to make that into a perfect square. And so you would you could do it that way too, just with the algebra. For the sake of time, I'm going to post this on Canvas afterwards so you can review the algebra that's there. But I just wanted to get you guys thinking about that because it will come up in lecture today. Number 2 and 3 on these warm-ups, they look like maybe they're a little bit challenging problems until you realize that we can approach these geometrically. To find the length along the curve, y equal to 3/4 x plus 1, well, this is a line. And we know the Pythagorean theorem tells us that the length of this line, a squared plus b squared, is equal to c squared. And so we can use the Pythagorean identity. If we find our change in x and our change in y, so our a squared plus b squared is equal to c squared, or in terms of our triangle here, our a would be our delta x squared plus our delta y squared, and that would be equal to the length of the curve that we are looking for. I call it L for length, quantity squared. And so we can solve algebraically when we find our x coordinates and our x coordinates are given -2 and 6. I think I did 2 and 6, so I should change this. Let's make this positive so that it lines up with the problem that I did in my solution. So from 2 to 6, then our change in x is 4. Finding the y coordinates gives us our change in y, and solving the square root of 4 squared plus 3 squared gives us the length along the line from 2 to 4, which is 5. And I bring this up because when we get into doing arc length today, this is the basis for the formula for arc length, looking at this Pythagorean identity and the relationship between change in x and change in y. And then the last one, just to show, you do know how to integrate. You could find the area under this curve, square root of 25 minus x squared. We will today talk about arc length, but falling back on geometry, we know that the circumference of a circle is 2 pi r, and when our arc length here is from 0 to 5, that's the portion of this circle that's in the first quadrant. And so a quarter of the circumference of this whole circle gives us 5 pi over 2 for the length of that curve. Okay, so that's all sort of gearing us towards the arc length and surface area portion of class today. The other thing, kind of going back to what we missed on Monday, I wanted to take a look at these two integrals. So on Monday, we integrated, that is not, let me fix that too. Trying to throw some new examples together for you. I need a 7. So if we change that 1 to a 7, then we should be good. Okay, so we found in lecture on Monday that the area under the curve from 1 to infinity of 1 over x squared dx, we found that that converged and it was equal to 1. So here I put a 7 in the denominator, and so this area would then be equal to 7 times 1 or 7. So the idea here is that the shaded area in red is under the curve 7 over x squared from x equal to 1 to infinity, is some finite number. It's equal to 7. So the area in blue, we know it's positive because it's above the x-axis. And we also know that it lies below the curve in red, which means that the area of that curve in blue, it should be something between 0 and 7. In other words, it should converge. Does that make sense, kind of how we explain that? Great, so that's the basis for the comparison test that we're gonna do. So let's jump back a second. Now I have to jump in my notes here. Okay. So the question is, algebraically, how do we prove that curve in blue? I think I did it in red. How do we prove that curve in red? No, I did blue. That it also converges. And so we rely on the comparison test. So I'll skip to case 2 because that's the one that kind of lines up with our warm up. So we had a curve, this was the 1 over x squared or 7 over x squared that we knew is convergent, and it has to lie above the x-axis. So that's where this 0 less than or equal to f of x less than or equal to g of x comes into play. That part is just telling us that it is a positive area. So we know we have some positive area lying above the x-axis, and that the area between some number a and infinity is finite. That's another way, if it converges, it is a finite number. Then if we have another curve that lies in between the x-axis and something that we know converges, then that curve also has to converge. We don't know to what it converges, but we just know that it converges. And for a lot of practical applications, that's good enough. Then the other side of this is diverging. So if we have some curve here in blue, and we know that it diverges, and then we have another curve, our g of x, and we know that it lies above f of x and the area under the curve, this area in blue for f of x, that's an infinite area. It's going to positive infinity. So then anything that lies above it on that interval will also have to be even bigger, meaning it diverges. So any questions on the comparison test? Okay. So when you are proving whether an integral converges or diverges using the comparison test, there's two things that you have to prove. So the first one is the inequality. You need to prove that one curve is smaller or bigger than the other curve, and they both have to be positive. The problem if they're not positive is, say down here in case 2, if we knew that the curve in red converged, but we didn't have that lower bound of 0, then the curve in blue, it could go off to negative infinity. So it could diverge to negative infinity without that lower bound. So that's why it's so important that you have that 0 down there as well. So the first part, you prove the inequality. The second part is you have to prove whether your compare to thing converges or diverges. So the compare to thing would be in each of these cases, it's the one that you know that you're trying to, and the idea here is that your compare to thing is going to be a P integral. You're going to try to find something that you can very easily prove whether it converges or diverges. And with P integrals, in our P integral test, you don't even have to integrate that. So it's a very nice, easy comparison to make. So let's do one. And for the sake of time, I have it written out for us, but I wanted to walk you through it. And I kind of have the thought process again in green. So that's not the things that you would have to write. That's just setting us up. It's all the things that go on within your brain before you start the comparison test, because you have to do a little bit of scratch work. So we have this rather complicated integral, and it's the one from my opening slide, my example. From 1 to infinity of 5 plus 2 sine x over x squared plus 3. And from our opening example, we know that's going to converge. And we also know that our compare to thing is going to be 7 over x squared. But how did we figure that out? So your thought process. The first thing you have to do is find your compare to integral. So before we even worry about inequalities or anything else, we have to find what are we going to compare it to. Now, normally the way you would find your compare to integral is if you had a rational function, a polynomial over a polynomial, you take the highest degree term in the numerator and the highest degree term in the denominator, and you simplify, you cancel them out, and that's your compare to thing. Here, our highest degree term in the denominator, that's an x squared. So we know that we'll have an x squared in the denominator. In the numerator, we don't have x term all by itself, but we do have sine x. And sine x we can treat like a number, because we know sine x is always going to fall in between -1 and +1. So it's always going to be some number. And we're multiplying that by 2 plus 5. And so a number isn't really going to change this relationship with x squared. So our compare to thing is going to be some number over x squared. So we're looking at, for now, we don't know what that number is, but let's just say 1 over x squared. Okay. So looking at this, we have to think, does this converge or diverge? And that tells us which way our inequality needs to go. Because this converges by the P integral test, it means that we need to prove that our thing, our function here, our integrand, lies between 0 and something that converges. If instead we had to compare this to something that diverged, say instead in the numerator here, we had x plus 5 plus 2 sine x. In that case, if we had an x up here in the numerator, then we'd have x over x squared, which when we simplify becomes 1 over x that diverges. And so if our compare to thing was 1 over x, we would need to prove that this was bigger than something that diverged. So that's the idea here, is we're looking, does our compare to thing converge or diverge? And based on that, how do we need to set up our inequality? So that's all of the thought process that you should do in your head before you get started on writing out your proof. So to prove the inequality, make sure you have your lower bound here, and then always deal with the numerator and the denominator in separate steps. That shows me that it allows me to follow along with your thought process. So it shows me that you know this is algebraically how it works, rather than just jumping to, oh, hey, this is my goal, so I'm just going to write that down. So make sure here, I'll write that in. Here we're dealing with the numerator. And then in the next step, separately, we're dealing with the denominator part of the inequality. So you want to always how did I say it? Just deal with numerator and denominator in separate steps. This is not a test of your algebra abilities. I know often that you can do it in your head in one step. The idea is that you are conveying to somebody else how the inequality is broken down. So because sine x is always going to be between -1 and 1, then we know that 5 plus 2 sine x is going to be always less than or equal to 5 plus 2 times 1, which is less than or equal to 7 for all x. So that is how you would deal with sine x or cosine x for that matter. And if you needed to add some extra steps in there, you could. You could start with bounding sine x by -1 and +1, and then in front of our sine x, we have a coefficient of 2. So then you can multiply by 2, giving you -2 less than or equal to 2 sine x less than or equal to 2. And then you could add 5 if you had room on the page. So we would have five plus 2 sine x less than or equal to 7. And the part that we care about would be the 5 plus 2 sine x less than or equal to 7. And so that's where I'm dealing with that numerator part of the inequality. And then in the denominator, we know that x squared plus 3 is bigger than x squared for all x greater than or equal to 1, in this case for all x. And so 1 over x squared plus 3 is going to be less than or equal to 1 over x squared. And so that's the denominator part of our inequality. And we can pull the 7 out front, that you don't have to. You could leave it as 7 over x squared. And you do need to say for all x greater than or equal to 1. And generally, this greater than or equal to 1, it will line up with whatever your lower bound is, but not always. So you should always just check, like plug in 1 into your inequality over here and make sure that it's true. Sometimes it might be true at 2 or 3, and that's totally fine. So as long as it's true for all x greater than or equal to some number a, it doesn't always have to line up with your lower bound. I do need your noses covered, guys. Thank you. Okay, so we have our inequality part done, and then we have to prove that our compare to integral converges or diverges. And we can use the p-integral test. Remember from Monday, we said there were 3 parts that you had to state for the p-integral test. The first is that it's a p-integral. The second is your value of p. So looking at your exponent, we have x squared, think p power, it's raised to the second power. So p is equal to 2, that's greater than 1. And if you're in a pinch and you don't remember the p-integral test, you can integrate this and you would get back a finite number and then it converged. But the p-integral test is a lot faster. So it's better to use this if you can. Okay, and then give your conclusion. So just like with the P integral test, just like with, we were proving whether something converged or diverged on Monday, we wrote out our conclusion. With the comparison test, your final answer should always be a written statement. So since, and you don't have to put the whole inequality, you just put the part that we care about. So our inequality is true for all x greater than or equal to 1. And you have your, whether your compare to thing converges or diverges. I put it down here twice in the hopes that you have it on your paper once. So you could, since you have your work up here, you could just say this converges, or this could be your work, however you want to, or you could put it in twice because twice is better, and then give your conclusion. So then our integral converges, and then name your test by the comparison test. I know I just threw a lot at you, and it's harder when I'm not writing because I go faster. Questions on this? Okay. So this is an example where our integral converged. The next example right after this is our integral diverges. So I wanted you to have one of both that you can use for reference. And then tomorrow in workshop, you'll have worksheets on comparison tests so that you can put this into practice. The other thing that I gave you is, I'll include it in the scribbles, my completed lecture notes for you, but this is a comprehension check. So this walks you through step by step what you need to do for the comparison test. So this is really nice to follow along with when you're doing your written homework or studying for an exam, because it kind of makes sure that you include all the little pieces. Yes. Oh, sorry, I can't. Can you say it louder? So he was asking, what if in this example, we had made the numerator, say instead of 7, maybe we had made it 8 or 9. Would that still be okay? Absolutely. I mean, I have had students where, they're just like, well, I'm just gonna put 1,000 in there. It maybe doesn't make your math as smooth, but yes, whatever, as long as the inequality is true, you can use whatever number up here you want to. Good question. Any other questions? Okay. The other thing I wanted you to make sure you take a look at, and I'll put this in the completed lecture notes, was one other example from Monday's lecture that we didn't get to. Monday, we were talking about when we had to break our integral up into 2 separate terms. Then how do we evaluate whether that integral converges or diverges? And so this is an example where we are evaluating each of the separate pieces or each of the integrals separately. And we found when you evaluate the first one that it does converge to 3/2. So you keep going. If the second one also converges, then our integral would converge to the sum of those 2 values. But since in the second case, the integral from 2 to infinity, here it diverges. And so that means that the entire integral diverges. And we can actually specify it diverges to positive infinity, knowing that one piece is going to positive infinity, the other piece is going to 3/2. So 3/2 plus something growing without bound is positive infinity. Now, if you lucked up and you had evaluated these in the opposite order, so if you had started with 2 and you knew right away that this was going to positive infinity, you can be done. Because no matter what the second piece does, you know that it's going to diverge. The only thing is, because you didn't evaluate the second part, all you can say is that it diverges. You can't say to what. And so in that case, if you only had this second integral here as your work, then you would just say that this integral diverges, and you would leave it as that. So this will also be in the finished notes, but you can use that as a reference too, but I just wanted to bring that to your attention. Okay. Now let's skip to our arc length. All right. Thinking back to our warm-up example with the finding the length of that line and thinking about it as our change in x times our change in y, or the square root of delta x squared plus delta y squared, we can approach finding the arc length for any curve in a very similar manner. So we can start by just looking at a segment on this curve. So let's say we just have just this one little piece, and we want to find that length. Maybe I won't do that just yet. Okay, so to find that length, using our Pythagorean identity, we make this into a right triangle. And so we know along our horizontal leg, this is going to be our change in x. And along the vertical leg, this will be our change in y. And so we can say that this length, this one line segment here, is going to be the square root of our delta x quantity squared plus our delta y quantity squared. Now, if we added up all of these little pieces, these little straight lines along the curve, so we have something along that idea here, then we'd be summing up all of those delta x's and delta y's, and that gives us the sum from I equals 1 to n of delta, the square root of delta x sub I quantity squared plus delta y sub I quantity squared. And the sub i's, that's just noting which one of these line segments you're on. That's all the I is standing in for. So now, to make our approximation even better, we want to make these little line segments smaller and smaller. And we do that by taking the number of intervals n and increasing them, which in math speak means that we have the limit as n goes to infinity. So now we have an infinite number of tiny little line segments that are getting very, very, very small, very short. And we're adding up all of our delta x sub I squared plus delta y sub I squared, that square root. So now let's factor out from underneath the square root delta, a square root of delta x sub I quantity squared. And that will simplify down to just our delta x. So this is equal to the limit as n approaches infinity of the sum from I equals 1 to n of the square root, and now we're factoring out a delta x sub I squared. So that first term becomes 1 plus, and our second term, we have delta y sub I over delta x sub I quantity squared. And then the delta x sub I that we factored out earlier stays outside of the square root. Now, I wrote at the bottom of the page, way back from Calc 1, the technical definition of an integral from a to b of f of x dx is the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x. So now what we have is the technical, this is equivalent, this is the integral from a to b of the square root of 1 plus dy dx. So that is the derivative of your function, quantity squared. And then the delta x that we pulled out of the square root, that's our dx. So this means that our integral is in terms of x. But we could have just as easily, instead of factoring out that delta x sub I, we could have factored out a delta y sub I. So if instead, factored out our delta y sub I, then we'd get the formula for arc length as the integral from a to b of the square root of 1 plus, and now we're in terms of y, so our function, we'd have x equal to something in terms of y, so we'd have dx, taking the derivative of a function in terms of x with respect to y. I said in terms of x, but taking the derivative of a function x equal to something in terms of y. That's the dx over dy, quantity squared. And we factored out the dy instead. And so we need a dy in the end. So that's the really nice thing about arc length, is that it's the same formula, whether you're given the function in terms of x or in terms of y. You do need to, I have them on the next page. You do need to memorize these. Memorize. And that's why I took the time to explain where this formula comes from, because I don't have these memorized, but I do know that arc length is the length of a little line segment, and the way you find the length of a line segment is the Pythagorean identity. And if we factor out that dx, then that gives us our leading term here of the 1, and then plus our y squared, our change in y squared, and that square root. So taking the time to maybe review where this formula came from would save you the process of having to try to put yet another equation in your head for memory. Okay. So example 1, it is a setup only problem. We want to set up the integral that will give us the arc length of y equals sine x on the interval from 0 to pi. So y is equal to sine x. That means our dy dx is cosine x. And our arc length is equal to the integral from 0 to pi of the square root of 1 plus our dy dx squared, so cosine x squared, dx. And for setup only, you can stop here. In fact, please stop there. Do not continue simplifying. Because that makes it more work for both you and me. So the way it's in this form, it's very easy to see, oh, this is the derivative, these are your bounds, and you know the formula. Questions on that? Let's do one that's a little bit more involved. So let's find the arc length of 1/8 x to the 4th plus 1/4 x to the -2 on the interval from 1 to 2. taking the derivative of our given function, we have dy dx is equal to, using the, I need to probably write smaller. We're going to run out of room. Dy dx is equal to 4 over 8 gives us 1/2 x cubed. Bringing the -2 down in front of the x and multiplying it by 1/4 gives us a -2 over 4, or 1/2 x to the -3. So our arc length is equal to the integral from 1 to 2 of the square root of 1 plus our dy dx quantity squared. So we have the 1/2 x cubed minus 1/2 x to the -3. That whole quantity squared dx. So this squared part here, I'll come over and just do a little bit of scratch work for you. So to square that, think of our FOIL method, our first, outer, inner, last. So we have so we're multiplying these two terms together. So when we multiply the first terms together, we have 1/2 times 1/2, which is 1/4, x to the 6th. When we multiply the outer terms together, that gives us -1/2 times 1/2 is 1/4, x cubed times x to the -3. The inner terms, we have -1/2 times a +1/2, which gives us a -1/4, x to the -3 times x cubed. And then for the last terms, when we multiply those together, we have a -1/2 times a -1/2, which is a +1/4, x to the -6. Now, in these middle two terms, x cubed times x to the -3, that's 1. Think of that as x cubed times 1 over x cubed. So that simplifies to 1, giving us 1/4 x to the 6th. We have -1/4 times 1 minus 1/4 times 1 gives us a -1/2. And then our last term is the 1/4 x to the 6th, x to the -6th. All right, so we can sub that into our arc length formula. One 1/4 x to the 6th minus 1/2 plus 1/4 x to the -6th dx. And under that square root, we have a 1 and a -1/2. So we're going to combine those terms. We're also going to write the terms in descending order. Giving us that our arc length is equal to the integral from 1 to 2 of the square root of 1/4 x to the 6th plus 1/2 minus, wait, do I have a plus? Plus 1/4 x to the -6th. Now that you've written it in descending order, you might recognize that this is from the opening slide. And again, I'll post the algebra if you want to find a common denominator and simplify it that way. I will post that approach for you on Canvas. But recognizing this as a perfect square means we take the square root of the first term, that's 1/2 x cubed. The square root of the last term, that is 1/2 x to the -3. And they're all positive, so we have a plus in the middle, dx. And if you go with this approach, just always check your work. FOIL your perfect square and make sure that you've done all of your algebra correctly and that it does line up. We have the square root of something squared, so those cancel out. We're left with the integral from 1 to 2 of 1/2 x cubed plus 1/2 x to the -3. And I will leave it to you, for the sake of time, to simplify that algebraically, plug in your bounds, but you should get 33/16. And remember, exact answers, so you should leave your answer this way, rather than as a decimal. One thing to point out, just taking a step back, big picture. We started with some function y. We took its derivative, we squared it, we added 1, we simplified, and somehow we got back something that we could still integrate. Now, the vast majority of stuff out there we cannot integrate. So in order to do all of those steps, you're going to find that these are very formulaic problems. You will start to see the pattern. And that's why I'm kind of pointing out that as you do more of these and become more familiar, recognizing them as that perfect square is often going to be very helpful for you because it's going to show up a lot. You might also look at the relationship between your derivative and our integrand once we fully simplified. Very similar. Look for those patterns. Now that I just pointed all of that out, let me show you an exception, something like secant y equal to e to the x. That is not going to follow that pattern, but it's not a polynomial either, so you can kind of tell off the bat. I'm going to skip this one because I want to talk about surface area, but this one you can integrate in terms of x or y, and either way you would get the right answer. Okay, so I'm going to tell you where the surface area formula comes from. Imagine that we have a cylindrical tube. So think about like a paper towel, that cardboard or for a roll of toilet paper, and we wanted to find the surface area. The easiest way to do that is to cut it right up one of its sides and lay it out flat so that you have a rectangle. And we know that the height of our cylindrical tube, we can call that h. And if it has a radius of r, then that means its circumference is 2 pi r. And so That gives us, for our rectangle, it will have a height of h and a circumference of 2 pi r. Length times width gives us area. So the surface area of the cylindrical tube is 2 pi rh. Now I point this out because in order to find the area of the surface formed by some function rotated about the x-axis or the y-axis, it's the exact same approach. So we rotate it around whichever axis we're asked to. And just like when we're doing integrals, remember we would make them into little dy, dx boxes, little rectangles, and add them all up. And for arc length, we did lots of little line segments and we added them all up. Here, we're doing a lot of little cylindrical tubes and we're adding up those surface areas. So let's take a strip, one of these cylindrical tubes. It's going to have a radius of r, and in relation to our curve, y equal to f of x, that means that our radius is going to be our y value. So if we're in terms of the y variable, our radius is just y. If we're in terms of the x variable, then our radius is whatever this function is. So our height now of our strip here, when we unroll it, we make it into a rectangle here, the height becomes the arc length. The length of the curve along that tiny little segment. And we have our radius, which is 2 pi r. And so multiplying the height times the circumference, arc length times 2 pi f of x, that gives us the overall formula for the surface area on our domain from A to B of our circumference times our arc length, relating that back to this is our circumference, the arc length being the height. So subbing that in gives us our formula. I better write it out for you. Of the integral from A to B, 2 pi r, and here our r is going to be f of x, so give me 30 seconds, times the arc length, 1 plus dy dx, quantity squared, dx, and this is in terms of our x variable. If we're in terms of our y variable, then we need y bounds from C to D of 2 pi. And now this is the important part. This is the hard part. Remember I said the radius, if you're in terms of the y variable, the radius is y. If you're in terms of your x variable, then your radius is whatever that entire equation is. Okay. And then from there, going back to subbing in the rest of your arc length, that is the square root of 1 plus. Now you're taking the derivative of x equal to something with respect to y, and the dy, nice easy way to tell us that we're in terms of y. Okay, so that's the kind of gist of where the formula comes from. You do need to have that memorized, and I will post these so you have examples, but you will get to work through this in workshop tomorrow as well.